Today's topic is principal component analysis. Before moving forward, let me explain you the concepts behind this so that it will be easy for you while we go through the slides. PCA is used to reduce the dimensionality of your data. Why? Reduce dimensionality, okay, of the data. Okay. So what is now the question is, what is the dimensionality? Okay. Reduce the dimensionality of the data. PCA. Okay. Assume that you have a data set, okay, where you have near about 20 features, okay, 20 features. Okay. What is the 20 features? It can be ID, okay, it can be name, then it can be education, income, okay, your housing, whether you own a rented house, you own a house or you are living in a rented house, okay. Assume that there are 20 features are there, okay. To support these 20 features, you have in the rows, means the number of records you are having around 200. That means 1, 2, 3. These are the number of records for the different persons or the data points. This is the 200. Assume that. Now this type is called curse of, okay, dimensionality, okay. Or curse of dimensionality. So what is the curse that this dimensionality gives you? That's when you have high number of features, okay. This is the features, right? ID, name, like that, columns. When you have high number of features and to support them you are not having enough number of data points, then we call it a curse of dimensionality, okay. So what is the support? Assume that at least to support 20 features, at least 1000 rows required. If you are having 10 features, at least 500 rows you require. That means you can multiply the features, number of features into 50. Those many data points should be there, okay. There is no hardcore rule, okay, but yes, when it is 20 to 100 or 200, then definitely there is a curse of dimensionality. So at that time, saving for you is the PCA. So what you can do? There are two choices. Either you can increase the number of records, okay, or you can decrease the number of features. Okay, there are two solutions to this problem. When you are not having enough data points, okay, or enough number of rows as compared to the number of columns, then the solution is these two. Either you can increase the number of rows or reduce the number of features. Increasing the number of rows, okay, this one, from where you will get data, and the new data added by you is accurate one, because this is not given by your customer, okay. Your customer has given you only 200 data and you are adding more data points by yourself, so there is no guarantee that it's authentic, and if that data point changes and if it's not authentic or not correct, your whole model will go wrong. Adding the data is never been a good solution, okay. So the next option, this is not the option. Why? Because the customer is given only 200 records, and if you add that one, that is to risk your model performance. Another solution is reducing the number of features. So the PCA exactly does the same thing, okay. What it does, reduce the feature. Why and how? Why? Because if you reduce the feature 20 feature, if you come to the feature 4 features, okay, 20 feature in the data set, and if you extract that which are your 4 main important features from the data, okay, and now you are having 200 data points, then there is no curse of dimensionality, because your data points or number of rows is more according to or with correspond to your number of features. One of the better solution that reduce the number of feature. That's what the PCA does. The curse of dimensionality is that you are given a data set where you have very high number of features, okay, like ID, name, income, where you live, okay, these are the column names, right? So you are having very high number of features, you are not having high number of the data points or the rows. Then it's called curse of dimensionality, because there are two dimensions, one is the feature, one is the data points. So at one dimension the feature it's very high, and to support it you are not having the other dimension. So that's why it's called curse of dimensionality. Solution is either increase the data points or decrease the feature. There is a little bit math involved, it's called eigenvectors, okay. People will ask you that what's the math behind it, but they will ask you how PCA does. Then you can only say PCA reduce the components by forming or by calculating the eigenvectors. Okay, so this part is enough, by calculating the eigenvalues and eigenvectors and its values. There is a math involved how to calculate. Okay, if we want to go through that or not. But for the interview purpose, it's enough. For your understanding, it's enough. Okay, so today's objective for this session, what's PCA, what's pros and cons, data standardization and case study. Okay, so what is PCA? PCA is nothing but the principal component analysis. Okay, it's a method for reducing the dimensionality of the data. Dimensionality reduction is to reduce the number of input variables for a data set. Okay, number of inputs, that is the number of features. Your PCA never ever reduce your data points. Okay, PCA, that part you understand very clearly. People will confuse while having the interview that what PCA does. Will it reduce the data points? Will it reduce the number of features? So PCA is a statistical technique to convert high dimensionality data to low dimensional by selecting most important features that capture maximum information about the data set. As I told you, from 20 to 4. Okay, very important of 4 features that will select. It's a hyperparameter, means you can give how many features you want. The PCA, the package will does the work for you, and it will select, give you only those 4 rows, or means those 4 columns, or 3 columns, or 2 columns, as per the number given by you. The features are selected on the basis of variance they can cause in the output. The variable which causes the max variance will be first principal component, followed by the second, third, so on. Okay. Assume that you are given a data set, okay, these features, okay, and these, and it is useful for both supervised, unsupervised. Okay, so there is no relation that the supervised it can use, unsupervised. It works overall. It uses for reducing the dimensionality for any kind of data set. Assume that it's the education column. Education is divided in 3 ways: undergraduate, postgraduate, okay, and graduate. And the income, okay, and the housing, okay, and the expenses. There are 4 columns, I am assuming. This one is education, this E, this I is income, H is the housing, where you live in a rented house or a own house. and this is the expenses column. Okay, if you see that in this data set, these four features are highly correlated with each other. How? Because it's very normal that if a person is more educated, okay, if education undergraduate, okay, three in this feature: undergraduate, graduate, and postgraduate. Three categories in education feature. Okay, so it's very likely that if a person's education is more, he will get a good job. Okay, if you learn more, then you will get a good job. When you get a good job, okay, your income will be more. Okay, it's obvious. So when income is more, it's a high chance that your housing will be a good one. You can own a house. Okay, in these two categories: own and rented. Okay, suppose it's a graduate or postgraduate, then the job means opportunity is good, then the income is good, and then housing, obviously, or not obviously, but most of the cases it will be like a person with 10 years of experience. Mostly he would be living in his own house rather than a rented house. Okay, so when your income is more, then there is a assumption that your expenses will be more, because this is the law of economy. When your income is more for a economy, then the expenses is also more. Okay, because you have more money to at your disposal, so that you can buy something which are not necessary living items, like luxury items. Okay, you can buy furniture, you can buy, a vehicle, all this. So if you see, these variables are related to each other. Okay, job, then to income, income to housing, and housing to expenses. In this data set, these four variables are highly correlated with each other. Okay, what PCA will do when you invoke a PCA, okay, it will look for the correlation between different features. And when there is a high correlation, okay, it will look for the, when you will invoke PCA, it will look for COR, or we call it correlation. Okay, so when you invoke PCA, it will look for the high correlation. How it will look for? I told you, with this eigenvectors. Okay, eigenvector is a mathematical thing. For the time being, you forget how it is. Each feature will be placed to one of the dimension. I can show you in a 3-dimension. Okay, this is the 3-dimension. If the data is having 3 columns, then it will be placed with suppose here, here, and here. It's a 3-dimension data. Likewise, if you are having 20, each column is having values, right? Some values under for each rows, that will be projected as a dimension. Okay, then for each dimension a single value will be calculated, that is called the eigenvectors, eigenvalues for each dimension. Then it will check that what's the correlation between the eigenvectors of different each dimension. From where we got this dimension? Assume that your data is having 3 features, because I can show you in a 3-dimension only. So assume that, or likewise you assume that there are 4 dimensions for our data. You assume 1 here, there is no problem at all. Okay, so it's a 4-dimension data. What it will do, it will education, whatever the column values are there, it will place it in a dimension. For income, it will create another data points or clouds of data. We call it clouds of data. So clouds of data will formed. From that clouds of data, for each the data cloud, one eigenvector will be calculated. Okay. Now it will check the what's the correlation between different eigenvectors. So to simplify it, don't go this side. Okay. It will be confusing. So go to this side. What PCA does, PCA tries to find the correlation between the features. Like I told you, education, job, income, housing, expenses, these are the highly correlated. So it will find a correlation. When it find that there is a high correlation between features, like in the example, job, income, okay, all these are highly correlated, then it will drop, okay, then it will drop the features which are very highly correlated and keep only one. Okay. Which one? It will be a new dimension. Okay. Which one it will keep? It will get the this eigenvectors and its values. Okay. So, and it will tweak it to give you only one dimension. We'll show you in a hands-on, then it will be clear like how the value is performed, means computed. But the theory behind it that it drops when there is a high correlation like education, job, income. Okay. So what it does, it drops the features which are highly correlated and keep only one. So in this way, it reduces the dimensionality. Okay. PCA takes the correlation between different features. When there is a high correlation, correlation high. When there is low correlation, then it will not be dropped, because you cannot, by keeping one when there is a high correlation, you can explain all the variables, right? If you keep your education field here, for example, then from there you can say that wherever the high education, high job, high income, own house is high expenses. When there is a high correlation, it drops all the features, keeps one. When there is low correlation, it has to keep the all the features. Advantages, if you see, the number one, removes the correlated features, or you can say high correlated features. Improves the model performance. Obviously, the curse of dimensionality is reduced. Reduces the overfitting problems. Yes, it reduces the curse of dimensionality is when solved. It reduces the overfitting problem and works great with the visualization and improved it. Why visualization it works? Because when there is 20 features, that means 20 dimension, you cannot visualize the data. If you reduce it to 2 dimension, then you can easily plot it, because our eye can see up to 3 dimension. Okay, disadvantage, information loss. Obviously you are reducing, so there is an information loss, but it is not that much significant. And standardization is must before PCA. Independent variables become less interpretable. Another very important step before proceeding PCA is that you have to standardize all your data. Okay, you go for the standardization. Okay, that is very important. Okay, this is D. Why standardization required? Okay, if you see in a previous example, okay, in the previous example, there is example that there is another column like number of years of experience. Okay, that is the experience, not expenses, rather experience. Because obviously if you have more experience, your income is more. So another column is there, suppose experience. See, another column is also we are having income. So the problem, if you remember, while going through the linear regression, that data set I told you, the problem is that when you have such features, your experience will be very less, like it will be in single digits, 1 year, 2 years, 3 years, whereas your income will be in thousands, 2000, or 3K, 4K, okay, 10K, like this. Actually, the model will not understand it's a income, so that's it's very high. It's a experience, it's 1, 2, 3. That's why for the model all the same features, right? Because it's not human language understandable. So whenever the high values are there for a column and low values are there for another column, it assumes that for those column it's having high value is a superior columns. So in this data set, if you model without standardization, model will assume that the income column is superior to the experience column. But this is not the case, right? Because all columns are important one for us. So to remove this problem, we go for the standardization. Okay. For all the values will be converted to -1 to 1. Okay. If you go for a standardization, it's a library, you can import it, standard scalar, model selection or something, standardization. There are two standardization methods. One is mean max scalar and standard scalar. Sklearn dot pre-processing dot standard scalar. Okay, you have to import like this from sklearn pre-processing import standard scalar. Once you import it, create an object. Okay, the third one, scalar equal to standard scalar, then fit the your variable x, then scalar dot fit. Okay, and transform. The third one, if you see, it's the fit the data and transform the data. Okay. Fit means it will fit it, transform will convert it. Okay. Another one is also there, pre-processing mean max scalar. Okay, the same thing, sklearn pre-processing mean max scalar. The same way you have to do it. Okay, scalar equal to, you have to create an object, scalar equal to mean max scalar after importing here, then print the data, means fit the data and transform the data. Okay, so what it will do, it will, if you see here, your features are there like 1 to minus 0.56, 0, 10, 1, 18, like this. It is converted to 0, 0, 0 0.25, 0 0.25, 0.5, 0.5, 1, 1, like this. Okay. So there is a high-low problem is solved with the standard scalar or mean max scalar. You must standardize your data before implementing PCA, else PCA will not be able to find the optimal number of principal components. Why it required, that's what is explained. If a feature set means the data is having kilograms, light years or millions, the variance scale is used in the training set. Okay, what's the variance? Like experience and income, there is a high variance, one is in single digit, another one is in the thousands. If PCA is applied in such data, the output loadings for feature with high variance will be large. As I told you, the model will understand with high value means it's very important feature. Hence, PCA will be biased. For standardization, all the categorical features are required to be converted into numerical features before PCA can be applied. Okay, and PCA is affected by scale, so you need to scale your feature. Okay, so scaling means the standard scalar and min max scalar, you can use it. Here is the summary with the steps on PCA. First, after getting the data, standardize. How to standardize, I have shown you. Okay, you have to import the sklearn pre-processing standard scalar or min max scalar. Use the standardized data to generate the covariance matrix. Okay, single vector decomposition, no need to do, only you have to import PCA. Obtain eigenvectors from the PCA, that also not required, the PCA will get it for you. Select the k eigenvectors with largest eigenvalues, only you have to give that how many principal components you require. Principal means important. Okay, principal component analysis, that means important components. 20 features, we are supposed to find 4 important features. Okay, feature means component. So construct a new matrix with the k eigenvectors. K is a hyperparameter, you can choose your own. Again the same library, sklearn, scikit-learn. Okay, if you see scikit-learn here left side, and you have to import the PCA like before we have done it. Okay, if you see here, from scikit-learn decomposition, import PCA, scikit-learn dot decomposition. Okay, PCA, if you see, the only input you have to give is the n components or the number of components you want it. The basic thing you have to pass it on. Okay, PCA, you are creating an object from the class called PCA. This one you have imported from the decomposition, scikit-learn decomposition. Only the parameter you have to pass that number of components you want, that is the n components. Okay, now after creating an object, you fit your data. Okay, your data here already into the same number, that's why no standardization required, but it's always great if you go with the standardization. So once you fit it, okay, PCA n components, then PCA you can go ahead and print the explained variance and the singular vectors. What is explained variance? That is your two components, how much percentage the data explained by your new component. If you see the new component, you have created two components here from the data, and the first component explains around 99% of the data. Okay, that means almost the data is explained by the first component, so there is no problem, right? Whatever is the dimension, you are reduced it to 2 and your data is explained with this 99%. This explained variance, it's a important one. After doing PCA, you always try to, the format is same, PCA dot explained variance hyphen underscore ratio, like this. If you give it, then you will get it. What's the percentage of your data is explained by your new components? Okay, if you see here, it is 99%, the first. That means the 99% of your data is explained with your new components. So there is no problem, almost all your data is explained. So you can go ahead with the new dimension. And after getting the PCA, this is not the solution. You can go ahead with your any of the classifiers. If it's a classification problem, go ahead with the classifier. If it's a regression problem, go with the linear regression. Okay, like this. PCA is only used to transform it to the lower dimension. It's not a AND solution. The parameters, it takes the n components. Okay, if you see the number of components, only you have to pass it what's the component you want, and rest all are not required. Okay, there is not at all required what all the parameters you will pass it, only pass the n components. It's all about PCA.